In this lecture, we are going to see how to write down a unique representative for each similarity class of matrix in a field. To begin with, let's look at the building blocks for KT modules. So if you have a torsion KT module, then it looks like M is equal to KT mod PT. Where PT is some monic polynomial of degree, some given degree d. So let's say PT is t to the d plus a1 t to the d minus 1 plus up to ad. So these are the building blocks of torsion KT modules, which are the kind of modules that you get when you look at KT modules corresponding to matrices. These would be the building blocks, and let's try to see what matrix this represents. So for that, just take any basis of M. So M, let's choose a convenient basis. We'll just take the basis 1 t squared t to the power d minus 1. So we can think of each of these as elements of KT and therefore also elements of KT mod PT. T to the d is linearly dependent on these vectors. T to the d is equal to minus a1 t to the d minus 1 minus a2 t to the d minus 2 minus all the way down to ad. That's because PT is 0 in M. And so now multiplication T acts on M by multiplication. And if we try to write down the matrix of this multiplication action of T on M, then what we need to do is figure out what does T do to each of these basis vectors. So T takes this first basis vector 1 to the basis vector T, and it takes the basis vector T to the second basis vector T squared, or rather the third basis vector T squared, and so on all the way up to T to the minus D, where T to the D minus 1, and then takes T to the D minus 1 to T to the D, which is no longer in our basis. However, it is given by a linear combination of our basis vectors as follows: minus a1 t to the d minus 1 minus a2 t to the power d minus 2 all the way down to minus ad. So the matrix multiplication, the matrix of this action of T is given by 0, 1, 0, 0. This is just saying that the first basis vector goes to the second basis vector. Saying that the second basis vector goes to the third basis vector is this, and so on. And the D minus second basis vector, or rather the D minus first basis vector, which is T to the D minus 2, goes to the D minus dth basis vector, which is t to the power d minus 1. And then t to the power d minus 1 goes to this vector, which I can write as minus ad minus 1 all the way down to minus a1. Okay, so what we have seen is that in the module KT mod PT, there is a basis with respect to which multiplication by T is the same as multiplication by this matrix. This matrix, by the way, is called the companion matrix of P. So CPT is defined to be this matrix. So it's just a matrix where you have this block. So you have this block which looks like the identity, and then you have over here this column which has all the coefficients of the monic polynomial PT, going from the units coefficient on top to the degree d minus 1 coefficient at the bottom, all with their sign reversed. So this is called the companion matrix of P. And the conclusion is that KT mod PT is isomorphic to M of CPT. Now, suppose we have two modules. We have a module M, which comes from a matrix A, and we have a module N, which comes from matrix B. For some, say this is an M by M matrix and this is an N by N matrix. MMK, B belongs to NMK. Then I claim that M direct sum N comes from the matrix with block diagonal matrix with block diagonal entries A and B. How do we see this? Well, the fact that M is isomorphic to M subscript A means that M admits a K basis with respect to which the action of T is multiplication by A. So let x1 up to xm be a basis of M such that T acts as multiplication by A with respect to this basis, and y1 yn be a basis of N such that T acts as multiplication by B. Then you can combine these bases to get a basis of M plus N. So M plus N, M direct sum N has basis x1 xm y1 yn, and with respect to this basis T acts as multiplication by A 0 0 B, and so M direct sum N is isomorphic to M A 0 0 B. So to summarize, we've seen that KT or PT is isomorphic to M of CP, where CP is the companion matrix of P, and we've seen that if M is isomorphic to MA, and so we can write it like this: MA direct sum MB is isomorphic to M of A 0 0, the block diagonal matrix. We can put this together to write down a form for any matrix now. So we know that given any matrix A belonging to M and K, we can write MA isomorphic to KT mod P1T plus KT mod P2T, and so on, where P1T, P2T up to PRT are all monic polynomials in KT, and P1T divides P2T divides PRT. Monic because these polynomials can be chosen up to unit, so you can always make the leading coefficient equal to 1. And so what we get is that MA is isomorphic to MCP1T direct sum MCP2T MCPRT, which is in turn isomorphic to, by this argument up here about direct sums, M And now you take the block diagonal matrix whose diagonal blocks are CP1T, CP2T, CPRT. Moreover, these matrices CP1T, CP2T, CPRT, well, the polynomials P1T, P2T, PRT are unique. So this form is also going to be uniquely determined by the matrix A. So what we have proved is the existence and uniqueness of a rational canonical form. Theorem. Every matrix A in M and K, so here we are assuming that K is any field, is similar to a unique matrix of the form CP1T, CP2T, CPRT, where P1, P2, PR are monic polynomials and P1 divides P2, divides P3 and so on. Okay, let's look at an example. Let's take the matrix zero, zero, 1, 0, 1, 0. And now the question is, can I figure out how to write this matrix in rational canonical form? So what we need to do is we need to take the module M subscript A and figure out its structure. So for that, firstly we write down Ti minus A, and that turns out to be T plus 1, minus 1, minus 1, 0, 0, minus 1, 0, minus 1, 0. And its Smith form is, let's see, so the GCD of all the entries here is just 1. So the 2 by 2 minors, well, most of them are 0, but let's see. Oops, I made a mistake here. There's supposed to be T's here. Ti minus A. So most of them are 0, but here's a minor which is T into T plus 1. Well, not most of them are 0. Some of them are 0, but here's T into T plus 1. Here's T squared minus 1. Here this minor is 1 plus T. So what you'll see if you compute all these minors is there are 9 of them, and their GCD is T plus 1. And the determinant of this whole matrix is, if you compute it, turns out to be T minus 1 into T plus 1 whole squared. So this third thing in the Smith canonical form is this divided by T plus 1, which is just T squared minus 1. So the Smith normal form of Ti minus A is this, which means that MA is isomorphic to KT mod T plus 1 direct sum KT mod T squared minus 1. And so A is similar to the companion matrix of T plus 1, the companion matrix of T squared minus 1, which is the companion matrix of T plus 1 is just minus 1, and the companion matrix of T squared minus 1 is 0, 1, 1, 0. So this is the rational canonical form of the matrix A that we have taken.